All right. So today we are going to continue with our discussion of reciprocity. And last lecture we talked about the basic idea that repeated interactions can stabilize cooperation. And the way that we talked about this was in the context of tit for tat, which starts by cooperating and then just reciprocates whatever the other person did in the previous round, which means that when two tit for tat players play against each other, they manage to get cooperation the whole time, whereas when a tit for tat player plays against a player that always defects, they only get taken advantage of on the first turn, and then they switch to defecting the rest of the time, and therefore the repeated interactions allows the tit for tat player to protect themselves against excessive exploitation, and in turn that creates an incentive for you to cooperate if you know that your partner is playing tit for tat, so that you can sort of get them to be willing to cooperate with you in the next round. And so as long as there's enough of a likelihood of a future round, then it's payoff maximizing to cooperate if the other person's also playing tit for tat. And so we sort of looked at how that could transform just a normal prisoner's dilemma payoff matrix like this into something like this, where basically instead of a social dilemma, it becomes a coordination game, where you can have a cooperative equilibrium and a non-cooperative equilibrium. And so what we're going to do in this lecture is we're going to, so basically the last lecture we talked about the strength of, or the advantages of repeated interactions for maintaining cooperation. This lecture we're going to talk about some of the limitations. So the first one is that in this discussion so far, we were only kind of imagining what happened when tit for tat played against a strategy that always defected. Now we're going to think about what happens if you also incorporate a strategy that always cooperates. And we mentioned briefly last time that the always cooperate strategy is essentially not taking advantage of the fact that repetition is occurring. And so when an all C player plays an all D player, they just, this all C player just gets exploited every time. But when we think about what happens in the context of adding all C to the interaction of tit for tat and all D, we'll see that things change a little bit. So when two all C players play, they just cooperate in every round. So in a 6-round game with this payoff matrix, they would just get 6 each time, same as when tit for tat plays against itself. And when tit for tat plays against all C, they all just cooperate the whole time. So regardless of whether all C is matched with tit for tat or vice versa, they're all just getting a happy 6 every time. And then when all C and all D are matched, all C is going to get exploited every time and get the sucker payoff, and all D is going to get the temptation payoff every time. So now we've got this 3x3 payoff matrix instead of a 2x2 payoff matrix. And what we see here is something which hasn't really come up in the lectures before, which is we've talked about looking at when one strategy can beat another strategy or not, but here we have something new, which is neutrality. So all C and tit for tat are neutral with respect to each other. That is to say, if you know the other person is going to play tit for tat, you do equally well to play either all C or tit for tat. So you can say you're sort of indifferent. And what that means is that in this game, tit for tat is not a strict Nash equilibrium anymore. Remember, the definition of strict Nash equilibrium is that you have to do better against yourself than anyone else does against you. And that's not true anymore, because now tit for tat against tit for tat is not better than all C against tit for tat. It's just equal. And so one thing that this shows is that whether you think of something as a Nash or not depends on what you're comparing it to. So in the game where we only considered tit for tat and all D, then tit for tat was a Nash, like a strict Nash. But once you add all C in, tit for tat isn't necessarily a Nash anymore. I mean, and more generally, that's a sort of obvious point that the way that we've been describing Nash, which is you do better against yourself than any of the other ones do, is going to depend on what the other ones are. But this neutrality makes a big difference, because if you think about the dynamics now, when we're just considering the interaction of tit for tat and all D, so if you sort of forget about that part for a second, and we project it down onto our sort of population line here, both tit for tat and all D are equilibria, And so that means if it's mostly tit for tat, it's going to go to tit for tat. If it's mostly LD, it's going to go to LD, and then there's going to be some kind of interior equilibrium where it's the direction of selection switches. And so if it was just those two strategies, this like line describes all possible states of the population. But now that we have a third strategy in there, there's a bigger population space. And so now the population is described not by a position on a line, but a position inside this triangle, where this corner is all tit for tat, this corner is all D, this corner is all C. The point right in the middle is 1/3, 1/3, 1/3. Say this point is like half all C, half all D. This is half all D, half tit for tat, and so on. And so now dynamics are not just flow along this line, but they're flow inside this whole sort of space of possible strategies. And so you can often get insight into what's going to happen in the middle by just thinking about what's going on the edges. So we already know what's going on this edge, that is considering the situation where only 2 of the 3 strategies is possible. So if we say all C is not present, then we're somewhere on this edge. It's just this game from before, and like we said, it's going to look like this. Now imagine what happens on the all C, all D edge. So you say tit for tat's not there. Ignore that row and that column. It's just all C versus all D, and you'll see that all D just dominates all C. That is, regardless, in both cases, all D is doing better than all C. It's just like a regular prisoner's dilemma. And so that means along that edge, no matter where you start, all D is always winning. Now think about what happens on this edge. So now forget about that, and you're just in this area of tit for tat versus all C. And this is where you get the neutrality going on. You just have, no matter where you start, that is, it doesn't matter, anywhere along this edge, the payoffs of the 2 strategies are the same. And so if you didn't have mutation, if you just had selection going on, there would be no selection. You could think of it in the definition of an equilibrium that we gave at one point, which is that the expected payoff of the 2 strategies is the same, that says any point along this line, that is any mix of all C and tit for tat is an equilibrium in the sense that they both are getting the same payoff. But once you start thinking about mutation, what that means is that if you're anywhere on this line, if you're anywhere along this edge, mutation is just going to cause you to sort of randomly drift around because there's no selection happening. And that can have some interesting consequences. And you'll see, first of all, the fact that this is neutral means this isn't technically a strict Nash anymore. It's just a sort of regular Nash. And now if we think about the dynamics, you can describe this by saying, instead of there being fraction P tit for tat players and 1 minus P all D players, now we've got 3 different types. You say P are playing tit for tat, Q are playing all C, and 1 minus P minus Q is playing all D. That is, the total still has to add up to 1. It's just now you've got 2 different things to differentiate. And so if this is our payoff matrix, the expected payoff of an all C player is P times 6 plus Q times 6 minus 6 times 1 minus P minus Q, right? So you've got probability that it's a tit for tat player, you get 6 when that happens. Probability it's an all C player, you get 6 when that happens. Probability that it's an all D player, you get minus 6 when that happens. Then for tit for tat, this part is the same, but there's the payoff for meeting an all C player or tit for tat player and an all C player is 6. But now when you meet an all D player, you only get minus 1 instead of minus 6. And now for the payoff for the all D player, when you meet an all, oh sorry, this should be backwards. Or rather, this is backwards. They should be switched. I'm just going to switch it so that I have it right next time. So with probability P, you made a tit for tat player and you get only 2. With probability Q, you meet an all C player and you get 12. And then with probability 1 minus P minus Q, you meet another all D player and you get nothing. So that term just isn't there. Okay, so now we can say for any point in this space, we can define the payoffs of the three different strategies. And if we imagine that the evolutionary dynamic is that strategies tend to increase if their payoff is greater than the average payoff in the population, and decrease if it's less than the average payoff. What it turns out happens is there's sort of two fundamentally different regions in this population space that have different dynamics. So if you're on this side of this line, this over here, it means there's little tit for tat. So remember, down here is all C, here's all D. Along this edge, there's no tit for tat. And if you're sort of close to the edge, it's mostly all D and all C, and not much tit for tat. And so that means everywhere in here, there's not enough tit for tat around to be effectively punishing all D. It's mostly just all C, and so all D dominates. And wherever you start in here, you wind up with all D winning. Whereas when you start on this side of the line, you get something that looks like this, where initially all D starts doing well because it's taking advantage of the all C in the population. But once the all C gets largely wiped out because they're getting exploited by the all D players, then you wind up back in the regime where it's basically just tit for tat and all D, and this line is sort of the point where when that happens, you're far enough over that tit for tat is the sort of winning equilibrium, not all D, and so it gets pushed back. Basically, all D gets wiped out and it falls back. And so, what this means is that this region in here is going to defection, but as long as you're starting anywhere in here, you're winding up with somewhere along this mix of tit for tat and all C, and that's cooperation. So that's fine. You say, okay, at this point, it's the same thing as saying, well, when you had tit for tat or all D, there were some initial conditions that would lead you to all D, but there was a big chunk of initial conditions that would lead you to tit for tat, and so we're still getting the evolution of cooperation, and so everything looks fine here. But now imagine, or think about what happens once you start somewhere in this region. Initially all D does well, then it gets wiped out, and you land on the edge. Once you include mutation, and so you take into account the fact that there's going to be neutral drift happening on this edge, if you wait long enough, just by random chance, the population is going to wind up drifting south of this line. That is, just through random chance, all C will eventually become common in the population. And once all C becomes sufficiently common, all of a sudden, all D can invade. And then you wind up in this equilibrium where drift can't take you out of it. And so it means that wherever you wind up starting, you're always going to wind up in defection. And so another way of thinking about it is all C, this sort of overly nice strategy, is like the Achilles heel of tit for tat.
When you say mutation, does that mean some things are not randomly switched between whatever is currently present, or like could I mutate TFT when I'm on the all C all D line?
Yeah, so it's a good question. By mutation, you can implement mutation in different ways, but in something like this, where there's just these three strategies, the idea would be that normally you think of the selective process as being the higher payoff strategies become more common. But what mutation means is that when an offspring is created, rather than being, sort of have the parent selected proportional to fitness, you pick a random parent. Or rather, not a random parent, because they don't even need to be there. You pick a random strategy. And so you could be that you're on the all D, all C line, and mutation could introduce a tit for tat mutant, which would shift it a little bit there. But still, it's not enough to get it out of the basin of attraction of all D. So this is sort of sketching out conceptually how this works. And then if we want to look at it actually quantitatively, I'm going to show this. We can use the differential equation formulation that I mentioned briefly a couple of lectures ago. Again, don't worry, you don't need to be able to do the differential equations. But this sort of general version of the replicator equation is if you have m different strategies, and then you have the frequency of each strategy is given by x of whatever the strategy number is, so x1, x2, so on. and then the frequency of the final strategy is 1 minus the frequencies of all the other strategies, then you can specify the evolutionary dynamic by saying the change in the direction of change or the magnitude of change of strategy xi is the current amount that's there times the current payoff of that strategy type minus the average payoff in the population. And then you can just numerically integrate this or solve it or whatever. And this is a case where there's just selection, there's no mutation. And if you add a mutation, just as per your question, to specify mutation here, so this is saying the only thing that matters for the change in a strategy frequency is the difference between its payoff and the average payoff. But you would just add another term that says regardless of the payoff, there's some probability that it that it comes into being. And so now you can numerically integrate it and make cool pictures like this. So this is, for that payoff matrix that I showed you, this is 100 trajectories, each one starting from some different point in the triangle. And so you see, for example, this one started down here with some mix, mostly all C, and then some tit for tat and a little bit of all D. But it was sort of like below this dividing line. And so all D just became more and more common as all C became less and less common. And then it hit the top where it was just all D. And basically all the all C got replaced by all D. And at that point it was within the basin of attraction of all D, so it just went there, and so on for all of these. Whereas in here you see that initially basically all of the all C gets replaced by all D. But then you hit the edge within the basin of attraction of tit for tat. And so you go all the way there, and for these, it just happens more gradually. And so you want it everywhere along this sort of chunk of that edge place that the evolution leads you to. But then again, if we added mutation, eventually it would drift down here and wind up there.
Oh yeah, that was my question. Given that it converges to the left, how was it that? But is that just because of law of large numbers, like in a sufficient amount of time, the neutral drift will drift down? Or?
Yeah, no. So it's that this formulation doesn't have mutation in it. That if you need mutation in order for drift to happen, if it's just the your payoff minus the average payoff is a change, when you hit here, everyone in the population is getting the same payoff. So your payoff minus the average is going to be 0, and so it just doesn't move at all. But if you introduce some amount of mutation, then you're going to wind up getting the drift in there.
By chance.
Yeah, exactly. Okay, so that's one problem with repeated with tit for tat as a strategy, is that it gets you can have neutral invasion by all C, or rather neutrality, and this is a concept called indirect invasion, which is tit for tat can't be directly invaded by all D, but it can be indirectly invaded by all D because tit for tat is neutral with a strategy that all D can directly invade. Whatever. Okay, so that's one issue. But another issue is the issue of mistakes. That is to say that in everything we've been talking about so far, we say a strategy specifies an action, and it always takes that action, and great. But in real life, often mistakes happen, which is you intend to cooperate, but you accidentally defect, or vice versa. This is something in the game theory literature. It's called trembling hands. That is, you go to cooperate, but your hand trembles and accidentally you defect. And actually, there's we saw in a lab experiment once, a literal trembling hand, where when we bring them into the lab and they play the games on the computers, we can see what's happening on all the screens, and because it's boring just sitting there, we'll just randomly watch people's screens and see what they're doing. And there was one where the people, they had gotten into a rhythm of they were just cooperating every time, so they would just click, cooperate, click, cooperate. But their mouse, because they weren't paying super attention, it was sort of drifting. And they click, and then he accidentally defected. But it literally was just a trembling of the mouse. Anyways, what this is a model of is the point that in life, accidents happen. It could be that it could be that you misunderstand what the other person needs, so even though you're trying to be cooperative, you wind up doing something that's bad for them. Or it could be that circumstances beyond your control prevent you from being helpful, even though your intention or your desire was to be helpful. And vice versa. It could be that sometimes you're trying to take advantage of a person, but you wind up doing something that actually helps them in the long run. Or that you try to to take advantage of them, but circumstances beyond your control change the outcome and things don't work out the way that you had planned. So if you think about the consequences of the errors for tit for tat, so you've got these, two tit for tat players, they're playing each other, they're both happily cooperating, everything's great, and then the first player makes a mistake. I'm going to use this little confusion thing to say they have trouble, and so they defect instead of cooperating. Now, the partner, this guy is going to say, well, he defected, so I should defect. And he's going to say, well, he cooperated, so I should cooperate. And so then you have this back and forth, a kind of like vendetta thing set off by this series of retaliations, essentially. And this is going to continue until, say, this guy accidentally cooperates, so it accidentally forgives, and then they get back on track with cooperating. Or it could be that this person accidentally, it could be this person accidentally defects again, and then they get into just mutual defection. And so you can see that mistakes really cause a big problem for tit for tat because they have the potential to derail cooperative relationships, basically because the whole point of reciprocity is retaliation. As a threat. So you shouldn't defect because if you do, I'm going to retaliate. Then if you accidentally defect, I'm going to retaliate, and it's going to be problematic. And you'll notice that the longer the games are, the bigger of a problem errors are going to be because the more likely it is that an error is going to occur. And so if you think about the payoff consequences for this, in this particular case, they wound up defecting basically half the time. And if you imagine what had happened if tit for tat was playing against all C, then when the tit for tat player makes this mistake, all C doesn't punish for it. All C doesn't care, it just keeps cooperating. And that means tit for tat gets to immediately go back to cooperating. And they both do substantially better. And so what this means is that once you put errors in, it's not just that all C and tit for tat are neutral, but it's that if you know that the other person is going to play tit for tat, you would do better to play all C than to play tit for tat so that you can avoid initiating vendettas. And so that means it's no longer neutral drift, but you get into a situation where all C actually dominates tit for tat. And so that means instead of this picture, once you add errors, it becomes even worse for cooperation because you have really strict dominance. And so now you don't even have to wait a long time for neutral drift to bring you down there. It's just wherever you start, you're going to wind up at all D. And so what we're going to spend the rest of class talking about is some potential solutions to this problem. And so one solution, which is, as you will see, turns out to not really be much of a solution, is a strategy called Grim. And Grim is a lot like tit for tat, except it's not forgiving. So Grim says, I will cooperate until a defection occurs by either player, and then I will defect forever. And so without errors, this is more or less equivalent to tit for tat in the sense that both Grim and tit for tat always cooperate when they play each other, and always cooperate when they play all C, and only cooperate in the first round when they play all D. And so without errors, they're basically interchangeable. But once you have errors, things are different. So if you think about what happens with errors, when Grim plays against itself, the minute a defection happens, both of them switch to defecting forever. So that's sort of worse than when tit for tat plays against itself. Grim does worse against itself than tit for tat does against itself, because forgiveness is good, or is useful when you're playing against a cooperative strategy. But you'll see that there's a benefit when Grim plays against all C. Then when Grim makes a mistake, he says, oh, well, a defection has happened, so I'm going to defect forever. And the all C player just keeps cooperating because they don't care. And so that means that errors allow Grim to exploit all C. And so here Grim does really well because he switches to defecting all the time, and all C just takes it. And so what that means is that even though Grim, when playing against itself, does worse than tit for tat playing against itself, because it doesn't have this ability to get back on track after an error happens, Grim playing against itself is much better than all C playing against Grim, because Grim exploits all C. And so that means that whereas tit for tat was dominated by all C, because all C's forgiveness, let it get back on track, that's not true for Grim. Grim dominates all C because it's able to take advantage of all C's excessive forgiveness. And so with errors, Grim is still in equilibrium, whereas tit for tat isn't. And so that makes Grim seem attractive. But if you think about what happens in longer games, and so let's go to the limit, and let's imagine an infinitely repeated game. So here the continuation probability is 1, because after every round, another round definitely happens. And so now we can't think about total payoff, because the total payoff is going to be infinite, because you're going to play an infinite number of games, but instead what we think about is the average payoff per round. So if you think about a game without errors, tit for tat and Grim are going to be equivalent, and so let's see what happens in a game without errors. When two all C players meet each other, they just cooperate with each other in every round. So in every round, they pay the cost C but give the benefit B to the other person. And same thing for all of these cooperative strategies. So the average payoff per round is B minus C for every round. And when two all D players play each other, they just get nothing every round. And when an all D player and an all C player meet in every round, the all C player cooperates and the all D player defects, so the all D player gets B and the all C player gets minus C. But now, if you think about what happens when all D plays against Grim or tit for tat, in the very first round, Grim or tit for tat cooperates. But then in every subsequent round, they defect. And because there's an infinite number of rounds, what happens in that first round doesn't matter, because it gets swamped out by the infinite amount of zeroness. And so that is effectively just 0. And so you can see that here, if it's just a world of tit for tat versus all D in an infinitely repeated game, tit for tat is really great. But now think about what happens if we put in errors. And here, because the game is infinitely long, the errors can be more or less infinitely rare. It's just extremely infrequently an error happens, but there's an infinite amount of time for the consequences of it to play out. For the unconditional strategies of all C and all D, basically it doesn't make any difference. I guess if I was being totally... so I'm going to assume that there's no errors for all C and all D, because that's a simple strategy. They just always cooperate. They always defect. And think about what happens for the tit for tat. If there's errors for tit for tat or Grim, that doesn't really matter. So for tit for tat, the errors, it turns out, are equally likely to derail cooperation or to revive cooperation. Because either you can accidentally defect when you meant to cooperate, which is going to initiate a cycle of the other person defecting on you, or you can actually accidentally cooperate when the other person defected, which is going to end the cycle of the other guy defecting on you and get back to the other guy cooperating with you. And so what that means is that in the long run, you are equally likely to be in any of the 4 possible combinations. And so the average payoff is going to be B minus C over 2. Basically, you're only getting cooperation half the time. And so you're only getting half the average payoff of all C. But still, against all D, you only cooperate in the first round, and then it's only these sort of epsilon, like super rare errors that you accidentally cooperate, and so it's basically just 0. But now, when tit for tat plays against all C, tit for tat extremely rarely makes an error, and then all C immediately forgives it. And so it's just like a little blip that goes away, and so it means that basically both of them just cooperate the whole time. And so now you see that the average payoff per round of tit for tat against itself is half that of all C against tit for tat. So here the errors are hugely costly, basically destroying half of the payoff that tit for tat gets against itself, and so all C totally dominates tit for tat. and so it's not Nash. If you think about Grimm, on the other hand, so all these cells are the same. Now, as soon as one error occurs, there's just defection forever. And so that means that playing against itself, it effectively never cooperates, because once an error is initiated, the infinite future of that relationship is going to be defection, and so whatever sort of initial amount of cooperation there was gets wiped out. And so basically Grimm is just all D. And so that means that it's not invaded by all C. So in that sense, it's still like a good strategy, but we don't get the evolution of cooperation. It just essentially turns into all D. Grimm is not a great solution to the problem of stabilizing cooperation unless the games are short, such that the mistakes don't have very much opportunity to really mess things up. So now what we're going to do is we're going to talk about a different kind of solution, and a sort of kinder, gentler solution, which is to say we want a way to get back to mutual cooperation after an error occurs. This is called error correction a lot of the time. And so one error correcting strategy that has gotten a lot of attention is called generous tit for tat. And so the idea of generous tit for tat is that after the partner cooperates, it always cooperates, just like normal tit for tat. But after the partner defects, instead of always defecting, it still cooperates with some specified probability p. So it sort of stochastically forgives a defection by the partner, or probabilistically forgives a defection by the partner. And so now, if you think about, this is our example of tit for tat against itself, where when in this case, an initial error starts vendettas, and then a second error of this guy accidentally cooperating resolves the vendetta. If instead it was two generous tit for tat players playing, now instead of having to wait until somebody accidentally cooperates, which would be very unlikely if errors are relatively rare, here every round there's some substantial probability that the person that is going to punish the defection will just forgive. And so it lets them get back to mutual cooperation much faster by being forgiven. And so that's great, and that means that tit for tat against itself does much better. Sorry, generous tit for tat against itself does much better than tit for tat against itself, because it's much faster to get back on track. And obviously, the more forgiving you are, the bigger this value of p is, the faster you get back on track. So that's great. But the flip side of being forgiving is it allows you to get probabilistically exploited by all D. If you think about what happens when generous tit for tat plays against all D, in the first round it cooperates, and then every one of these subsequent rounds it cooperates with probability p. And so that means that being more forgiving both allows you to get back on track quicker, but also makes you more exploitable by all D. And so you can do a calculation balancing out these two different factors, and you come out with that. It turns out that the optimal value of p is the cost of cooperation divided by the benefit of cooperation. And when you're at this perfect amount, this is what the definition of this is this is the highest possible value of p that allows you to resist invasion by all D. So if you were more forgiving than this, then you're too forgiving and all D can invade. And if you were any less forgiving than this, then you would not be getting as good a payoff when playing against another generous tit for tat player, because you sort of wouldn't be forgiving enough. So this is like a cool solution in the sense that it enables you to get a much better payoff against yourself than you would if you were just playing regular tit for tat. But as long as p is less than 1, if you think about all C is like the version where p equals 1, right? Where it says no matter, I always cooperate after the other guy defects. And so as long as p is less than 1, which is basically always going to be the case in order to not be invaded by all D, it's still going to be the case that all C is going to do better against generous tit for tat than generous tit for tat does against itself, because that's just like the ultimate level of forgiveness. So this doesn't really solve the basic problem of errors making all C dominate conditional strategies. And so there was a bunch of excitement for generous tit for tat because it makes some intuitive sense and also it's simple. But the sort of current favorite strategy of game theorists for playing games with errors is called win, stay, lose, shift. And the idea of this strategy is it says if you got a bad payoff last time, change what you did, and if you got a good payoff, keep doing the same thing. And good or bad is defined as follows. There's 4 possible payoffs. This is the RSTP thing, right? There's 4 possible outcomes. And if it's the prisoner's dilemma, it's defined by this ordering that the best thing is you defect while the other guy cooperates, followed by mutual cooperation, followed by mutual defection, and worst is you. Sorry, that should be the other way around. It should be C. The other guys. Sorry, let me just fix that. And then the worst is you cooperating when the other guy defects. And so what win, stay, lose, shift does is it says these 2 are good outcomes and these 2 are bad outcomes. So if one of these things happens, keep doing the same thing. If one of these happens, switch. And so that means if you successfully exploit the other person, great, keep defecting. And if you successfully get mutual cooperation, great, keep cooperating. If you both defect on each other, that's not great, try cooperating. And if you get exploited, that's not great, switch to defecting. This is also called Pavlov, because it feels a little bit like Pavlovian conditioning kind of thing. And so to look at how this works, and just to say another way of saying the same thing is that win, stay, lose, shift says if you both do the same choice, then cooperate, and if you don't do the same, and if you do different things, then defect. And to look at why this is great, imagine what happens in this case that the 2 win, stay, lose, shift, they start. Oh, and also it starts out by cooperating. Forgot to say that. So they start out cooperating. They both get the good outcome of mutual cooperation, so they keep cooperating. Then once the first guy makes a mistake, in the next period, this guy says, well, hey, I got a good payoff. I was able to exploit that other person and let me keep defecting. And this person says, hey, I got a bad payoff because I got exploited. I should switch and I should start defecting. So they both defect. And then, in this period, they each say, hey, well, we got the bad payoff of mutual defection, so maybe we should try cooperating. And then, boom, they're back on to mutual cooperation. So that means that win, stay, lose, shift does very fast error correction. It doesn't have to wait for some kind of probabilistic thing to happen. It's just like mistake, mutual defection, boom, we're back on track. And even more importantly, think about what happens when win, stay, lose, shift plays against all C. They start out mutual cooperating, it's great, things are looking neutral. Then win, stay, lose, shift makes a mistake. And so in the next period it says, hey, I successfully exploited that person, great, let me do it again. And all C doesn't care, they just keep cooperating. And so win, stay, lose, shift just sticks with defecting. And so that means win, stay, lose, shift isn't neutral or invaded by all C, but is able to figure out, this is a person that I can successfully exploit. So win, stay, lose, shift is good at cooperating with itself and is good at taking advantage of all C. But if you think about what happens when win, stay, lose, shift plays against all D, it's not that great. In the first period, win, stay, lose, shift cooperates and all D defects. So win, stay, lose, shift says, oh, that's bad, I got exploited, let me switch to defecting. And then says, oh, that's bad, let me try cooperating. Says, oh, that's bad, let me switch to defection. Oh, that's bad, let me switch to cooperating, and so on. And so win, stay, lose, shift gets exploited in half the rounds. And actually, I think it was in one of Axelrod's tournaments, someone put this in, and it was called Simpleton, because they said it's so dumb, because it just keeps cooperating half the time. But it turns out that if you think about an infinitely repeated game with rare errors, say what's the average payoff per round, win, stay, lose, shift can actually do real well, because so now if you think about it, when it plays against itself, it gets cooperation in basically every round because the error is immediately corrected. Well, in two periods. And when all C plays against win, stay, lose, shift, it gets essentially defects. All C cooperates and win, stay, lose, shift defects in every round. So it's basically like the all D payoff against all C. And so if you do the equilibrium calculation on this, you can see that in this case, win, stay, lose, shift is a real equilibrium. It can't be invaded by all C, and it can't be invaded by all D. And so that means it's this sort of good real solution that it error corrects, and so it does well against itself. It does it very quickly, and like generous tit for tat, it also gets exploited by all D. But the fact that it does well with itself can balance that out, so it can be an equilibrium against invasion by all D. And the biggest difference is that it also dominates all C. And so even with errors in an infinitely repeated, like very long game, you get win, stay, lose, shift being an equilibrium. And so this is why, and not only does it match, but it maintains basically 100% in equilibrium. So win, stay, lose, shift is like the great solution to how to have cooperation repeated games with errors. And that was sort of where the game theory literature sat for, something like 10 or 15 years or something like that. And then as someone that is interested not just in the theory, but also in actual human behavior, when I was in grad school, I was thinking, well, this is great, but there's only one problem with win, stay, lose, shift, which is the theory looks totally great, but it's completely psychologically implausible, because the key part of win, stay, lose, shift, what it makes it work so well, is that after mutual defection, it switches to cooperation. And how many of you are going around and every time you two people don't like each other and have some negative interaction, you're oh yeah, we should try cooperating. I was there's no way that is a thing. And in the model, it's great because it sort of serves the secret handshake is the way I think about it, two win, stay, lose, shift players being oh, if you both defected, that's our cue to go back to cooperating. But that's not a thing. And so we did these experiments where we brought people into the lab and we had them play repeated games where there was a 7/8 continuation probability after every round, and we did it for different the cost ratios, and we looked at what strategies they used using various different analysis approaches. And and I should say they played games with errors, where every period there was a 1/8 probability that your move would get switched to the opposite, and you would only find out what the other person did, not what they intended to. So basically, we implemented the model in the lab. And what we find is there's no evidence of anyone using win, stay, lose, shift at all. But instead, what people were doing were strategies that what we call of being lenient or slow to anger. So, for example, there's tit for two tats, which says, rather than saying, if you defected last time, I will defect, they say, I'll cooperate unless you defected for the last 2 periods in a row. Or there's a version of a Grim with a delayed trigger, as I say. So Grim says, I'll wait until there were 2 periods in a row where defection occurred, and then I'll defect forever. And so these strategies are error correcting, but in a more psychologically plausible kind of way. And we also found that as the returns to cooperation increased, people were more likely to be lenient and more likely to be forgiven, which makes sense because the higher the payoff of mutual cooperation is, the more beneficial it is to be able to preserve a relationship. So the more willing you are to give the other person a second chance, because it would be more beneficial if you were able to get back on track. And so the point of this is that, and I should say also, in these experiments, these lenient strategies were actually also the ones that earned the highest payoffs. So it wasn't that the people were being altruistic, and in fact we showed it wasn't correlated, leniency wasn't correlated with altruism. It was just a good strategic move that in repeated interactions with errors, it's actually in your self-interest to be forgiving, at least up to a point, so that you don't miss out on the value of good relationships. You don't allow your important relationships to get derailed by mistakes. So to summarize, mistakes are a big problem for reciprocal strategies, because they initiate retaliation and have the potential to derail these otherwise productive relationships. And that means that it's somewhat self-interested to be, or rather, it's self-interested to be at least somewhat forgiving. And what the experiments showed was that people got this, but they were actually a little bit more forgiving than the theory says is optimal. That is, there could be some weird strategies that could have exploited the strategies that people in the lab were playing, and nobody learned to do that. And one possible explanation for that is that in real life, there's also like, you have more ways of knowing the other person's intention than just the outcome. You have some access to what they intended to do. There's third-party observers helping keep people aligned and so on. But whatever. The key point is mistakes mess up reciprocal relationships, but that can be fixed through being forgiving. And so next time we're going to move on from pairwise repeated interactions to group interactions between groups where reputation is at stake.